Welcome. In this video, we are going to review the great paper Volumetric Rendering with Baked Quadrature Fields. So basically that's a really nice paper, for example, for rendering, well, it can render at up to 500 FPS, but of course it depends on the resolution. At 1080p it can render at 100 FPS. So basically the main idea of this paper is to leverage mesh, but not leveraging mesh in the traditional way. So for example, they will bake the NeRF into a mesh, but then you cannot, for example, take the mesh and plug it in any rendering software. Unlike other approach that used that baked NeRF in meshes, we will see some comparison with those methods later in the paper. Here, really, the idea is to go from the observation that GPUs over the last decade or the last decades have been developed to do rasterization, to compute a triangular intersection very efficiently. So basically the idea is just to use that, to use the fact that GPUs are very good at that task, and therefore they are very good to work with mesh, and therefore we are going to use mesh in our work stream, but not to use them in the traditional way. So for example, when we do a traditional rendering with NeRF, so I assume that you have some knowledge about NeRF. If not, I invite you to have a look at all my other videos. But basically we shoot a ray in the scene, then we need to sample points along the ray. So usually we do that first with a uniform sampling, and then with a not rejection sampling, but important sampling, yeah. So basically after having some points, we can evaluate the density and do important sampling. So that's really the basics of NeRF. Here the idea is to say, okay, I will define my mesh so that my mesh will represent what we call quadrature points. Well, so that my mesh will give me quadrature points. So I will train my mesh, or I will design my mesh so that when I shoot a ray through it, all the intersection with the mesh are what we call my quadrature points. These are the points where I need to evaluate the quadrature equation for doing the volumetric rendering. So basically that will give me those points. At those points I will get the color on the density, and then compute my line integral, and that will give me my my pixel value. And therefore we can model very complex complex surface. For example, we can model fur, hairs, we can model transparent surface, which we cannot do very easily with standard mesh. We need a lot of triangles. So that's really the big takeaway from this approach. They leverage mesh, but not in the way they were designed. Well, yes or no, but basically not in the standard way. They just take advantage of the fast triangle intersection between rays on a mesh. So basically how the training goes, first they train a NeRF. So basically first they pre-train a NeRF. And then what they will do, they will train an intermediate neural network, which they call the quadrature field. So basically that's a neural network where the zeros of this function f will tell us which point we need to sample. So basically a bit like Siren, a bit more like surface reconstruction method like News, for example. We train a neural network on the zeros of that function, give us where we need to sample points. And basically once we have this function, so that we train from the NeRF model, so basically when the NeRF model has a lot of density, so maybe we have a plot about that. So when there is a high density, that means you are hitting a surface, and that means we need to put we need to put a zero there because we are at a surface and we need to sample points over there. So okay, we train this quadrature field, so its zeros are where we need to sample points. It's where the NeRF model is high density. And then based on this function, we can run the ray marching cube algorithm to get a mesh. So we extract a mesh from this function. The issue of this mesh is that it was extracted from the quadrature field, but it was not optimized directly with the photometric loss. So with the RGB, the MSE loss between the RGB from the real image and the predicted RGB image. So here what they are doing, they are refining the mesh, so they are producing a deformed mesh by training it with the photometric loss between the real data and the re-rendered data. So yeah, you can really see that it is it could be omitted, but that's really a way to enhance results. Because this mesh was extracted from this quadrature field that was itself extracted from the NeRF model, so there is some kind of loss of information due to the optimization, which is not perfect, onto the fact that this mesh was not extracted directly from the images, from the real image. Here we fine-tune it in order to displace the mesh. That's a common approach in, for example, approach that learn 3D mesh, for example. They do not optimize the vertices directly, but they learn a deformation field network. So basically that's a neural network that tells us the displacement in R3 of each vertex. So once we've learned this function, we can deform the mesh, so get our new mesh that has been updated. And then basically we can bake that. So basically, well, the baking, I'm going to explain that in a bit. But yeah, once we have our deform mesh, we can save it into file, and then we can use it as I just explained. We can use the mesh so that for each ray we compute the intersection and get the quadrature points, and then you can compute the volumetric rendering equation. So now to compute the volumetric rendering equation, for each point we need the density on the color. The density we can easily bake it, so for each triangle, for each triangle we store the opacity. But what we also need is the color. Unfortunately, the color we cannot bake it directly because the color is it's view dependent. So basically we don't need to store a single value or a vector of values, but we need to store a function. An efficient way to do that in a rendering, it's to use a spherical harmonics. So I made a video about that. So for example, the PlaneOxel paper is based on spherical harmonics. So I invite you to have a look at my video on PlaneOxels if you're not familiar with them. But basically, spherical harmonics are coefficients that you learn. And then when you receive a new view direction, so theta and phi, you can compute the color by using the coefficient. It's as if you are learning the function ax plus b. And therefore you are storing the coefficients a and b. So basically here for each triangle, it's as if we were storing the opacity and then the coefficients a and b. And now when we receive a new direction, we can compute the color by doing ax plus b. As you might expect, the function is a bit more complicated with a bit more parameters than just a and b. It depends, it can go from 16 parameters to 25. I think these are the commonly used values, but sometimes it can go to much higher value. You can have much more values than that. But let's say that you have 25 coefficients plus the opacity. That means that for each triangle you are storing 26 values. Sorry. So that means that now you just need your parameterized mesh. So by parameterized mesh we mean the mesh with the opacity and with the coefficient for each triangle. And then we shoot a ray in the mesh. We compute all the intersection with the mesh, all the intersection with the triangles, and then we can compute this equation. And therefore, we are really leveraging the GPUs, or they were designed. We are leveraging the mesh. And here we have some example. Here, for example, with mobile NeRF, that is also leveraging mesh, but mesh cannot handle a transparent object. On here, by not using mesh in the way they were designed to work, or at least by modifying modifying how they are used, they can model transparent object. They can also model fur on hairs, as you can see here. You can see the difference between mobile NeRF and the method. Here the level of details is very impressive. Here the fur, it's also super impressive. You can compare it to the mobile NeRF approach. This one is also doing great. I'm not sure. Okay, it's instant NGP, but of course slower. And I believe less detailed than the method. And here we have the ground truth. So very awesome method. Okay, here we have some results. So that's it for this video. I really hope it was helpful too, that it gives you some idea about implementation, about products. Do not hesitate to reach out if you need help with your project, and do not hesitate to subscribe for more content related to NeRF.